Okay, we're going to be using the Tarbuck, Lutgens, and Tasa. These are the authors for the textbook we'll be using for Earth Science. Remember, this is Honors Earth Science. This is a dual credit class. You get both high school credit and college credit. You will get 4 hours of lab credit that transfers wherever you're heading at the next level of education. Here's an online textbook. You can click on this link, and you will see that we are going to be using the term Earth as a system, Earth system science. This is going to be a recurring theme in this class. That an important occurrence in modern science has been the realization that Earth is a giant multi-dimensional system. Our planet consists of many separate but interacting parts. A change in any one part produces changes in any or all the other parts that can be neither obvious or immediately apparent. Although it is not possible to study the entire system at once, it is possible to develop an awareness and appreciation for the concept and for many of the system's important interrelationships. And that's kind of what this class is about, in building an awareness and just understanding where things come from and how we got here. I think those are two really good driving questions. Environment, that's everything that surrounds and influences an organism. These can be small and large scale. The physical environment of the water, the air, the soil, and the rock, along with conditions such as temperature, humidity, and sunlight, among many others. And resources, these are great value to people. These include water, soils, metals, and nonmetals. These build our societies and are what we use daily. Resources, we have renewable and non-renewable resources. Really, we're looking at the timeline in which they can be replenished. Short periods of time, we can look at solar power or solar energy. We're really looking at how we derive energy and run our societies, run our world. Solar energy, wind energy, hydroelectric, right, moving water, biomass, and geothermal, right, using the heat from the inside the earth. But we have non-renewables, and these are what we call our fossil fuels: oil, natural gas, and coal. And then nuclear energy is a technological form or way in which we go about harnessing energy as well. But these cannot be replenished in short time spans. So roughly 84% of the total amount of energy used globally comes from fossil fuels. So therefore only 16% does not. So as our planet continues to grow, so does our need for fuel and energy. So if we look at a population growth curve, we can look at this as, historically speaking, right, this is from 0, so from BC to AD. We're looking at this very, well, let's just say a plateauing, kind of a gradual incline or increase in population growth. And then recently, we've got this explosion. So our population dynamics, right, today we're above 7 billion. And it's, well, let's just say when we start reaching up here in the 9 and 10 billion people threshold, you know, that's in your lifetime. The Earth has a carrying capacity of 9 to 10 billion people. And this will take place in your lifetime. So we can't ignore that the Earth that provides everything for us, that, well, let's just say humans are in the mix and things are changing. The 4 domains in Earth science that we'll be studying in this class, the scope and scale include oceanography, meteorology, astronomy, and geology. Here we can look at the Earth's place in the cosmos. And a really cool storyline that goes with how and where it all came from is about 14 billion years ago, an incomprehensibly large explosion sent all the matter of the universe flying outward at incredible speeds. After a few billion years, the material cooled and condensed into the first stars and galaxies. Because the universe is expanding, the evolving galaxies continue to move away from one another. About 5 billion years ago, our solar system began forming in one of these galaxies that we call the Milky Way. Right? We live in the Milky Way galaxy. We're on this outer fringe of this spiral galaxy. And if we rewind time, we can trace all points in all matter, right? The stars you look up at the night sky, and some of those dots you see are actually galaxies, but they're just so far away, we see them as one point of light. But if we rewind time, here's 5 billion years ago. This is when our solar system began its earliest evolutionary phase. If we rewind time, 10 billion years ago, 12 billion years ago, all matter, if we could rewind time, all matter would be traveling back towards one another into one point. And this one point in time that began it all is what we refer to as the Big Bang. So the Big Bang is kind of the origins of the cosmos. Be careful The Big Bang is not what generated our solar system. Our solar system is relatively young compared to the timeline of the cosmos. So the nature of scientific inquiry. We've been able to take a look at Gaian science, right? Earth system science. That was in my lifetime. This was considered, let's just say, fiction, false, fake. And now it's actually readily accepted. We look at paradigm shifts, how new information changes the way scientific communities and ourselves and how we view the world. Stupidity in science is essentially researchers, people looking and diving into the unknown. We don't have the answers. That's why people do research. They ask questions. And last but not least, research-based science. This class is going to be based on modern and contemporary science, scientific models, data, and calculations that prove or that support, maybe not quite prove, but support that the information that's in here is scientific, it's testable, it's quantifiable, it's reproducible, and it's verified by outside sources. Very important that we make sure we are looking at this science class as verified by outside sources. It's reproducible. It's not something that somebody dreamt up and published. It's definitely scientific. So we'll be doing these. We'll be having some practice with inquiry, right, where we ask a question. That's actually what inquiry is. We come up with a hypothesis. Then we come up with a theory. We experiment it. We collect data. We make sense of that data and we draw conclusions. And wherever those conclusions take us, we then go about retesting a new question that the inquiry or the question led to. And that's really the nature of science. So within the textbook, it talks about, here's a picture. I really like this picture, right? The atoms in these minerals, right? This mineral is made up of atoms. Well, these formed, right? The atoms in the mineral that formed the rocks of the earth were formed in stars, exploding in supernova. Stars build atoms in their cores, right? So the atoms that are in your body actually, that compose you and compose the earth, were actually built, literally, compressed in the cores, or heat and temperature, or excuse me, heat and pressures squeeze hydrogen into larger elements. There are billions of galaxies that contain billions of stars. All of these findings are the result of inquiry. Scientists asked questions and they sought answers, and they found a way to go about scientifically testing them. Here's a really cool video that Neil deGrasse Tyson, my favorite astrophysicist, it's a video we'll watch in class. Pretty cool. Give you some perspective. And how the earth formed. Right, we go from this gas, dust, material. It begins to gravitationally pull itself together. It begins to organize itself here in letter C. We start having these regions in space. The sun got 99% of all the material. The remaining 1% was scattered among space. And then that area, right, Mercury, Venus, Earth, we'll say this space right here, the third region, is where the Earth acquired all of its matter from. And it gravitationally coalesced or built upon itself gravitationally and built the location in space where the Earth is today. Pretty cool storyline. We'll be looking at the Earth's spheres. Hydrosphere, right, water. Atmosphere, gases. Biosphere, where we find life. And geosphere, where we find the solid, rocky portions of the Earth itself. Earth's interior structure. We've got a crust. We actually have two different types of crust. We have oceanic crust and we have continental crust. We have the mantle. The Earth is mostly mantle. We have a liquid outer core and we have a solid inner core. And we'll get into the science behind how we know this to be the case. Here we have Pangaea, the most recent supercontinent. And this is what it would have looked like about 200 million years ago. And here we're looking at plate tectonics. Plate tectonics is a really basic idea. Oops, I didn't mean to do that. And we'll be studying this pretty much in depth. We'll be studying the convection, just a form of heat transfer. Earth system science, how do we separate or merge processes together? Hydrologic and the rock cycle is an example. And so when we study a hydrologic cycle, we'll study this individually. We'll study the rock cycle. And then we'll decide and we'll determine how this interplay of the two, actually, they're working simultaneously together. And then last but not least, I always find it an interesting concept to just say, you know, the Earth finds a way and life finds a way. That doesn't always include humans in the process. And in this case here, a picture of Mount St. Helens. and then a picture of it many years after it is revitalized and finds a way to go about surviving.